Hello and welcome. This is a heat engine problem. We'll first try to solve the problem manually, at least show the algorithm for how to solve the problem, and then go to test and use a suitable test step to solve the problem very thoroughly and set it up for parametric studies. So first of all, the information given here are that the heat engine operates between these two temperatures. These are our temperature, hot temperature and cold temperature of the engine. It produces net power, it's given to us, W.external or W.net, and Q.h, the rate of heat transfer, is given. So therefore, first question is find the thermal efficiency. We all know thermal efficiency is the desired output, which is W.net, required input, which is Q.h. In this case, it is simply 200 by 400, so 50% or 0.5. The fuel consumption rate in kg per hour. So the fuel consumption rate is what? You burn fuel to maintain the hot reservoir at TH. So the hot reservoir is losing heat at 400 kilowatt. So therefore, the fuel consumption rate in kg per second is what? Is 400 kilowatt is what you're supplying, and divide by the heating value of the fuel, which is 400 divided by heating value is 45 million joules. So we convert that to kilojoules per kg, and this should give us fuel consumption rate in kg per second, and you have to multiply that by 3600 to get kg per hour. To find the minimum possible fuel consumption rate for part C of the problem, which produces the same output. So work output will be still 200 kilowatt, and if we can improve the efficiency of the engine, of course Q.h will go down. We don't need as much heat if the efficiency is higher. And what is the maximum possible efficiency? Is the Carnot efficiency. So we'll find Carnot efficiency is 1 minus Tc over Th, and in this case, Tc, Th being supplied, you can show that it will 0.85. So once we know Carnot efficiency, we know the minimum Q.h. So Q.h minimum will be 200 by 0.85. And once we calculate minimum heat requirement, we can again divide by the heating value and come up with the minimum fuel consumption rate. Well, we'll put all the nitty-gritties into the test code so that all the numbers will come out and you can verify later on. For the sake of brevity, let's move on to test. I have already logged in as a student. Okay, so to launch a suitable test step, we go to the test step page, and we are analyzing a closed steady system, which is a cycle. So this will be our desired app. So we go click there, and the leftmost tab is it launches the app. So as you can see, we could enter the variables such as Q.h, TH, TC, etc. right here. Instead, let's solve the problem more neatly. So what we'll do is we will enter all the known variables. So we'll write a comment line first of all. Comment line begins with the hashtag. We'll say given variables of the problem, given information. So let's see what are given to us. First of all, Q.h in kilowatt is given to us. Note how I include the unit in the variable name. That's a very good practice because to keep track of all the units in a problem. W.net kilowatt is given, 200. What else is given? Okay, I've already listed all of them in a separate tab to save time. So these are the given information. And notice the variable name I have picked. Instead of calling it temperature of the hot reservoir, I have picked THK, which is a good practice because in the state panel, you'll notice TH is the variable name. Again, clicking the calculate button will bring all the variable has been read and registered. You can see their values here. So now we are going to substitute this variable. I'm control C to go to the state panel, click on the variable name, it turns it on, and I'll just say equals, and I'm pasting the variable name instead of typing it in. So to go back and forth, you got to click the calculate button. That way the variable name has been registered here. Again, I'm bringing up what is w.net given to us, equals this, and calculate. So you can see w.net is known, and these are easy to type in. So I can just do thk, and notice that the 0 doesn't bother, the software takes care of it. tck, right? tck, and we do the calculate, and just to make sure, if there is a mistake, it will not, suppose instead of thk we typed in a variable that has not been declared, then when you calculate, you will find this is a white background. That's how the mistake get detected. Another important thing to remember is that to make sure that you declare things correct, you can just put the pointer over the variable name, and once you do that, you can see that there is this, keep an eye on this area. So when you move the pointer over, when you move the pointer over a variable name, you will see the value appear right there. So tck is 300 Kelvin, thk is 2000 Kelvin, just like we have specified. All right, so already we can see a lot of information has been obtained, a lot of results have been obtained, but let's be neat about it. So first of all, we write a comment line that what is wanted. So we'll say thermal efficiency, this part A of the problem. This is part of the answer. So let's call it eta thermal, which is, of course, we have already calculated. This is a part of state 1 of the engine, eta thermal 1. If I do a calculate, you can see that it's 50%. Also, you can see that how a variable that's in the state panel has been imported here. So state panel has eta thermal 1 actually, and that's recognized in the IO panel. Now, let's write another comment, control C, control V. This time, part B is what? Fuel consumption. All right. So what we know about this, first of all, the heating value is given in, by the way, it will be a good idea to begin a variable name with lowercase letter, unless it's a standard symbol. So we'll call it heating value in kilojoule per kg would be equals what? I copy the million joule per kg variable and multiply by 1000. And if I do a calculate at every step, you can see the heating value is 45,000, which is correct. So now we can find the fuel consumption rate, which is m dot fuel kg per second would be what? Is the heat required, which is Q dot H in kilowatt divided by heating value. So heating value, the fuel consumption rate is found at the bottom. You can see that the question asks for fuel consumption rate. Let me again control C, kg per hour. Oops. Fuel consumption rate in kg per hour equals kg per second times 3600. If I do a calculate, the answer is found 32 kg per second per hour. Finally, I've already solved the last part here, so I'll just go over them quickly with you. The minimum fuel consumption is what? We have to find the maximum efficiency, eta max, which is eta Carnot 1 by 100. Notice that Carnot efficiency is given to us in percent. So we have to divide by, actually Carnot efficiency is not given, it has been calculated in the state panel. Eta Carnot is 85%. So what we are doing, we are dividing eta Carnot by 100 to get eta max. So Q dot, the hot reservoir, the Q dot minimum in kilowatt is the net work that is being produced divided by the maximum efficiency. So this is the minimum heat requirement. So now we can calculate the minimum fuel requirement in kg per second, following the same process as we did in section B. And finally, we get the minimum fuel consumption in kg per hour, multiplying by 3600. So all the answers are displayed here, at the output area. So, well, now that we have solved the problem using TESTapp, why have we done all this work, extra work, for a simple problem? The beauty is that now all the variables of the problems are exposed here, and we can change any of their values and do a what-if study. For example, right now we know the minimum fuel consumption rate we calculated is about 18.8 kg per hour. And the question, suppose we are just thinking that, well, the hot reservoir is 2000 Kelvin. We know if the hot reservoir temperature is higher, Carnot efficiency is higher. Suppose we say, okay, what if it was 1500 Kelvin? So just see how easy now to solve the problem again. We just change the hot temperature to 1500, everything else remaining same. Click the calculate button, which means this value is now registered, and come up here and click the super calculate button. What it does, it updates all calculations. No matter how complex the problem is, all the variables will be updated, and minimum fuel consumption rate is now 20 kg per hour. See, the fuel consumption rate went up because the highest temperature we reduced. So like that, in any kind of problem, if we expose all the variables, if we isolate all the variables of the problem here and take advantage of the state panel and import the variables here, like for instance, we imported eta Carnot, we imported efficiency, etc. from the state panel. And we can make quite a complex, quite a sophisticated solution in this manner.